Any general questions, problems, anything? Okay, then that brings us to essentially the end of acids and bases, though not the end of equilibrium. Although, good news, bad news. We're a week away from the end of equilibrium also, so hopefully by now my mantra has sunk in, and we know that all equilibrium problems have three parts. Of late, really the focus has been on what to do when you have multiple reactions going on, right? And part of the big reason for that is the water issue, by which I mean water is both an acid and a base, right? And so in the context of acid-base chemistry, there is virtually always multiple equilibriums going on, right? Quite frankly, even if I just have an acid and water, I have two equilibria because there's Kw, right? But as I have said several times, and as we've seen just recently, typically water is not my target molecule for any of the chemistry I'm doing. It's there, right? It does its Kas and its Kbs and its Kws, right? It's the sole reason for this whole pH obsession with acids and bases, right? But typically, if I'm doing acid-base chemistry, I am taking an intentional good acid, right, and an intentional good base at the very least, and mixing them, right? At which point I have four reactions, right? Because there's the acid and the base with each other, there's the acid and the base each with water, and then there's good old Kw, right? And so, especially with acids and bases, this idea of having multiple equilibria occurring, right, is virtually, almost 100% of the time, right, what I'm doing, even though, again, there's probably one reaction I really want to do, and the other ones are more or less in the background, right? A perfectly good illustration of this, right, and really, my favorite way to sort of wrap up acids and bases is by talking about titrations. Right? Titrations are a more general chemical analytical technique, right, where I intentionally do a reaction where I know the concentration of one of the reactants, right, and I can use the stoichiometry to determine the amount of the other reactant, right? And so it is frequently used to determine an unknown concentration of some chemical species, right? In the case of acids and bases, of course, my reaction would be an acid-base reaction, right? So, for example, if I took sodium hydroxide that I knew the concentration of, I could titrate a solution that has an unknown concentration of quite possibly an unknown acid, right, and use the reaction as a means of essentially counting the molecules of acid that are present, right? In general, any titration really requires that I have two things, right? A balanced chemical equation, right? And some way of knowing that the reaction is exactly over, right? By which I mean you can, of course, arbitrarily mix random amounts of anything and you'll get a reaction. But if I'm mixing random amounts of anything, I'm not getting any quantitative information from it. And so I have to know that I've exactly and completely reacted each of the two reactant molecules with neither one left over, right? In some sense, I need both reactants to be limiting reactants. In more complicated parlance, I need a stoichiometric ratio of the reactants. In the case of acid-base reactions, which I believe somewhere along the line in lab you've done the titration, right, there's a couple ways you could know that you've reached the end of the reaction. A lot of times it is identified chemically because there is a pH change that occurs near the end point. And so because there's a fairly abrupt pH change, which we'll talk about more in a minute, if you have another chemical compound, which is technically a dye, that is pH sensitive, you can tell that the pH changed. You can also, in fact, directly measure the pH, right? And the issue really boils down to this, right? If I start with my solution of unknown acid, it's going to have a pH less than 7. How much less than 7 is going to depend on how much acid, right? And frankly, how strong an acid it is, right? A little bit of HCl, which is a strong acid, goes farther than a little bit of acetic acid, which is a weak acid, because down here, at the moment, all I've got is Ka as the dominant acid-base reaction. And so how big K is will kind of determine what the pH is. So the pH alone won't tell me how much acid is there, right? But the titration will, essentially because I introduce another acid-base reaction, right? I'm intentionally now adding a better base than water to get them to react. And so in pictorial form, right, I essentially get a quote unquote neutralization reaction. I've represented it as hydroxides and H pluses, although again, there's no reason why the base has to have a hydroxide, but a base in water, right, does generate hydroxide because at the very least there's a KB reaction up top and there's a Ka reaction at the bottom. And what I've really done by mixing them is introduce a K neutralization reaction, right? Whether my base is hydroxide containing or not, right? When I mix the two together, I'm going to get a neutralization reaction, right? And as I keep adding it, I keep quote unquote neutralizing the acid. And so the pH keeps going up, right? As I get closer to the end point, the pH is sometimes 7, right? But as I get close, what I'm going to have is essentially a rapid change from being less than 7 to being more than 7, right? Because at this point, I'm acidic, but just barely acidic because I have very little proton concentration left, right? At this point, as we will see shortly, right, my pH is not necessarily 7, but what it is doing is approaching more than 7, right? Because as soon as I've added a little bit of excess base, now essentially the dominant reaction in the bottom beaker is now the KB, because the only thing I have left is that excess base, right? And so if you actually plot what that looks like in terms of the actual pH, right, the curve looks something like this. As again, we'll see in a moment, this is more representative than it is exact for every possible acid-base combination. But what you get is a fairly gradual change in pH initially, and you get a very gradual change in pH at the end, right? But in the middle, you have a much more rapid change in pH, right? And that's really the log nature of pH, right? After all, my pH is a log scale. So what it really cares about, right, is powers of 10, right? Well, if you're down here, right, your concentration, you know, is going from 10 to the minus 1, right, to, you know, 5 times, well, it's going from 5 times 10 to the minus 1 to 2 times 10 to the minus 1 to 1 times 10 to the minus 1, right? It's a very gradual change, even if I'm adding a fair amount of hydroxide, right? Remember, I mean, my endpoint here is essentially, right, I'm going to call it 0, right? It's really, of course, essentially KW, right? If I'm in water, I'm never going to have actually 0 hydronium. But what I have is no excess acid other than the water, right? And so near the endpoint, there's very little, right? So when I'm over here, I'm now 10 to the minus 7 molar hydronium, you know, and a little bit earlier, I'm 10 to the minus 6, and I'm 10 to the minus 5. Very little amounts of hydroxide are making factors of 10 change in the acid left, which is why you get that really sort of sharp rise near the endpoint, right? A little bit of acid, excuse me, a little bit of base when your acid concentration is 10 to the minus 1 doesn't change the concentration that much, whereas that same amount of base when your concentration is 10 to the minus 6 has a much bigger change in how much hydronium is left, right? And so the numbers will change slightly, as we'll see for the rest of class today, but the general trend is true, right? If I'm titrating an acid with a base, right, I'm going to get a somewhat gradual change initially when I have a lot of acid, right? I'm going to get a gradual change at the end because now I have a lot of base, a lot of extra base that I've added. So a little bit more doesn't change the pH very much, but I'm going to get a very rapid change when I'm near the endpoint. All right. And so this is really why my pH indicators like phenolphthalein work, right? Because I don't have to turn color at exactly this point. If I'm up here, I'm down here, I'm only a drop off, right? And so I have a fairly wide range of pH values within which, as long as my colored indicator changes color, I know I'm at the endpoint. Right. The other thing about my fancy curve here, right, is I don't necessarily need a separate indicator to determine when I've reached the endpoint, right? Because essentially, sorry, a little math speak for you, the math phobic, so trigger warning. Right, the actual endpoint is the inflection point of that curve. Right, I mean, you start out with a relatively gradual slope, right? When you get near the endpoint, the slope starts accelerating. And at the inflection point, it then starts decelerating, right? And so, you know, if I take the second derivative of the curve, right, the second derivative equals 0 at the inflection point. And so one way to know where the endpoint is to actually just stick a pH meter in it, right? Measure the pH as you add your titrant, right? Plot it and use Excel and a little bit of math to find the inflection point of that curve. That's actually called the potentiometric titration, right? And if I do that, right, my graph of pH versus either acid or base added, or really for a non-acid base titration, simply titrant added, right? In general parlance, right, the titrant is the thing you're adding to induce the reaction with what's in the beaker, right? But for an acid-base reaction, my pH versus titrant added, right, is called a titration curve. Right? When I'm actually doing a titration in the lab, right, I don't necessarily know what both chemical compounds are. Right? Again, I certainly should know what the titrant is, right? It gets back to you've got to be really lazy or really incompetent to not know what's in the beaker. Right. But if I'm titrating literally an unknown sample, which is why I titrate things in the first place, I may not know what the acid is, right? A lot of analysis is done, for example, on wastewater, right, or groundwater, looking for contaminants, right? In that case, I had no control over what went into the sample. And in this case, all I'm trying to figure out is how much acid in the sample. I don't necessarily know or care what the acid is. Right. So in general, I don't really know exactly what that curve should look like. On the other hand, if I do know what the acid and base is, I can calculate that curve, right? Because that pH value comes directly out of the kind of calculations we've been doing. Right. I've got 2 acids and 2 bases in my beaker almost at all times, right? So I'm going to have multiple acid-base reactions, right? One of which is going to result in a pH, right? And so I can calculate the pH at every point in the titration. And of course, you know, if I add an acid to a basic solution, it does sort of the same thing, but in reverse, right? The pH is going to start high because there's base in my beaker, right? As I add acid, it's going to gradually change, then rapidly change through the equivalence point, and then flatten out again. Right. For reasons that will become clear in 5 minutes, right? The pH at the equivalence point is 7, but only if the acid and base that you're titrating are both strong, right? So in this case, if I'm titrating HCl and NaOH, right, both of which are strong, HCl is a strong acid and NaOH is a strong base, I will have an equivalence, right, at pH 7, right, but only because they're both strong. And you can see this in what, say, mostly boring set of calculations. And I say boring because, of course, if I got strong acids and strong bases, I got friggin' big Ks. And so for the most part, I don't have a lot of equilibrium going on. Right. And so, you know, I'm going to do a very sort of non-titration thing, right? Because again, my titration is usually designed for me to determine something I don't know, right? But I'm going to essentially calculate what my theoretical titration curve should look like if I know that I have a strong acid and a strong base, and I actually know how much I have of each one of them. Right. And so to that end, I'm going to start with 50 milliliters of the strong acid, and then I'm going to gradually add NaOH to it and see what happens to the pH. Right. Again, as I'm fond of doing, right, NaOH, I mean, HCl obviously an acid, NaOH obviously a base, NaOH also a salt, right? So again, the first thing I always want to do is dissociate my salts, because essentially the sodium part of it is really a spectator, right? It dissociates when it dissolves. It's not really sodium hydroxide, it's sodium and hydroxide. And as we've seen, the sodium doesn't really do anything, so it's really just the hydroxide. So it does make my life easier to sort of get it out of the way. You can, in this case, sort of leave it there if you want, but again, you end up with this somewhat non-physical sort of high school version of this, where I've got these salts as aqueous species when, again, they're really not. And so again, I usually think it's clearer to write it this way, right? But if, you know, if you write it that way, certainly a lot of people will. And so I want to do the strong acid, strong base relatively quickly. As I say, it's kind of boring, as you'll see once we get going, and leave some time for the weak acid. Right. And so initially, all I've got is HCl and water. Right. And again, like any other acid-base problem, you know, ice chart, K equation solve. But the fact that it's a strong acid sort of takes all the fun out of my equilibrium problem, right? Because my K is freaking big. So it's essentially a limiting reactant problem. I could still make an ice chart if I want. Obviously, I did, right? But again, the signature of my limiting reagent problem is something goes to zero. Since it's HCl with water, and water is the solvent, the HCl has to be the limiting reagent, right? And right, what that gives me is an equal amount of hydronium, because again, remember, pH is always the concentration of the hydronium, it's not the concentration of the acid, even though for strong acids, it's a little deceptive because it's the same number, right? And so, as a starting point for my pH, the pH is the negative log of the 0.1 molar hydronium, and so I'm starting at a pH of 1. Right. And then I'm just going to start adding sodium hydroxide gradually. Right. So I suggested 10 milliliter aliquots. And so I'm going to add 10 milliliters of 0.1 molar sodium hydroxide. Right. Again, at this point, you know, my analysis of the problem, which is always based on what are the acids and what are the bases, right, has changed because I now have 2 acids and 2 bases. And so technically there's 4 reactions. And so, hey, that's no big deal. I just do them in the order of K. And the biggest K here is for which reaction? The what? Well, the HCl in water is freaking big, but which reaction will always have the biggest K if I have multiple acids and bases? Well, it's the K neutralization. It's the biggest Ka with the biggest Kb. There may be more than one K neutralization, right? In this case, right, the HCl has the biggest Ka. It's freaking big. The biggest Kb is sodium hydroxide. The biggest K is actually the K neutralization, which is super freaking big in this case. technically freaking big squared, right? And so, right, I now have more than one reaction I may need to consider. There's good old Kw at the bottom, but along the way, there's K neutralization, then there's the Ka of the HCl with water and the Kb of the NaOH with water. But I'll just take them in order, you know, and what's second, third, and fourth really depends on what's left after the first one, right? And my first one, again, is kind of boring because it's super freaking big, right? So it's a limiting reagent. The limiting reagent is the hydroxide. There's less of it, right? And so again, my signature for any limiting reagent problem, the limiting reagent goes to 0. So 0.001 minus x equals 0. So x is 0.001 everywhere. So I have less HCl. I now have chloride. All right. Thank goodness chloride's a spectator. I don't really have to worry about that. Right. I can't do anything else with the hydroxide. So the only reaction I actually have left, well, I have 2 left, but the only reaction I'm going to ultimately care about is the Ka of HCl. Again, there's Kw at the back. Should I need it, but I still have so much HCl, I'm not going to need it. Right, and so again, technically, the HCl reacts with water, but all that means is 100% of the HCl dissociates because it's a strong acid, which means I get exactly the same amount of hydronium. Right, again, I'm trusting you to note that. Right, you'll also note there's a slight dilution going on because I've added 10 milliliters of aqueous sodium hydroxide. So my volume is increased as well as my HCl decreasing. Right. And so the pH has crept up to 1.17. Right. Again, this is what I predicted earlier. Right. There should be a gradual change initially. I mean, notice I lost 20% of my acid and the pH changed from 1 to 1.2. All right. Yes, no. And frankly, not a lot terribly exciting or different happens for a while. So if I add a little bit more sodium hydroxide, I'm going to end up with a little less HCl. HCl is still a strong acid, so it completely dissociates. And again, the volume keeps creeping up at the same time that essentially the hydronium is going down. And so the pH keeps creeping up, right? I've now neutralized 40% of my HCl, and the pH still only went from 1 to 1.4. Right, if I do it again, I've now lost more than half of my HCl, and I'm only up to 1.6. All right. If I do it yet one more time, I've now lost 80% of my HCl. All right. And I'm still not quite at 2 for a pH. Right. And again, that's largely because I have not changed decades in my number. Right. I had 0.00 something of HCl the whole time. Of course, even a little bit of acid now, or excuse me, a little bit of base, and my acid is going to be down to 0.000 something, which is why the pH starts to rapidly change here. I'm going to very quickly go through multiple powers of 10 in the concentration with a little bit of hydroxide. If I had more time, we could calculate more points. I'm just going to add another 10 milliliters of 0.1 molar sodium hydroxide. That actually takes me to the end point. Right, at this point, technically, both the HCl and the NaOH are the limiting reagents because I end up with 0 of both of them. Right. And so, technically speaking, I have no HCl, I can't do any HCl reactions. I have no NaOH, I can't do any NaOH reactions. But I do still have water, so I can do Kw. Right, at this point, the only source of hydronium is the Kw, and so, right, all of a sudden, that equilibrium matters. It's never very big, but when it's the only thing in the beaker, right, and if I solve good old Kw, I get a pH of 7. All right, that is why for a strong acid and a strong base, I do get a pH of 7 at the equivalence point because it's good old Kw again. Remember, that's where that pH of 7 for quote unquote neutral comes from to begin with. All right. If you'd like the actual equilibrium solution, right. At this point, things get boring again. Right, I'm still adding sodium hydroxide. I now have no HCl for it to react with. So in fact, all I'm really doing is essentially making a sodium hydroxide solution. Right, I keep dumping sodium hydroxide into the beaker. There's nothing for it to react with, and so it just sits there. Right, but of course, right, it's a strong base. Right, technically there's a Kb for it. Right. But again, as we've always done with bases, right, I can essentially get the hydronium concentration from good old Kw again, or 14 minus the POH. And so, hey, look, all of a sudden, I am massively basic. Right. But at this point, once I've got a significant concentration of hydroxide, if I add a little bit of hydroxide, again, I continue to increase the total volume. I'm now increasing the amount of hydroxide. The pH starts gradually creeping up again. All the drama is over. And so, as I predicted, even in relatively large steps, I can see the basic pattern of my titration curve. I have a gradual change of pH. At the beginning, it very rapidly changes from 2 to 12. Right. If I filled in more points, you know, I would find that it pretty much goes from 4 to 10 in a few drops of NaOH. And then it flattens out again as I'm just gradually increasing the amount of hydroxide. Right. So as advertised, something like this with, in fact, again, a pH of 7 at the end point. All right. Now, of course, as I've at least implied previously, that's only true for strong acids and strong bases, right? If I've got weak acid or weak base, or God forbid both, right, then I actually have equilibrium problems in Ks that need to be solved, right? So that kind of changes the math. It doesn't change the basic strategy. Ultimately, I still have multiple acids and bases. All of them can react with each other, and I treat them in terms of smallest K to biggest K, right? So I will titrate acetic acid with sodium hydroxide, right? It's more complicated if I had a weak acid and a weak base. On the other hand, there's really no reason for me to ever do that, right? Because I get to choose the titrant, right? I have no control over what's in my sample sometimes, right? If you brought me a sample of pond water from, you know, parking lot, well, any parking lot, we're surrounded by swamps, but right, U lot, the U-lot swamp, I don't know what's in it, right? And so it might very well be a bunch of weak acids, but what I can always control is what the titrant is. I decide what goes in the burette. And so typically I would always choose either a strong acid or a strong base to do my titration with, so that I don't have the problem of having too weak species where I have multiple equilibria all the time. Right. And so again, you know, sodium hydroxide, still a salt, I still dissociate it. In the end, I still have a list of acids and bases. Right. The only difference is, right, this now is weak, whereas before it was frickin' big. I'll put sodium over here, it's just a spectator. Right. And again, same basic issue, right? Biggest K first. Once I start the titration, the biggest K is once again K neutralization. The best acid is acetic acid, even though it's weak. The best base is still the hydroxide, right? And that still has a super freaking big, right? K, because of course, right, this is freaking big, but freaking big times this divided by 10 to the minus 14 is super freaking big, right? And so my lead reaction is the titration reaction, which is my weak acid with my strong titrant. Right. And essentially, I'm doing exactly the same thing I was before, except, right, when I do my titrations and there's acetic acid laying around, unlike the HCl, which was strong, the acetic acid is not, so I do have a K equation that needs to be solved, right? And I can see that right from the very beginning because, hey, when I've got nothing but acetic acid in water, I've got nothing but acetic acid and water. And so I really have two reactions, this and KW. KW not so important here. All right. But unlike before, I do have an equilibrium I need to solve. My assumption here works. This, in fact, again, is our very first acid problem, 0.1 molar acetic acid. So assume X is small, cross multiply and take the square root. Right, I have a pH of 2.87. You might notice right off the bat, it was the same concentration of acid, but for the weak acid, right, the pH is going to start higher because I don't get complete dissociation of my weak acid. So already the shape is a little different than it would be if it was a strong acid and a strong base. All right. And then I'm going to complicate my solution by adding a second base, the sodium hydroxide. But again, that just technically gives me 4 acid-base reactions. And as always, I just do them in order of biggest K to smallest K. In this case, the biggest K is the K neutralization. That one is super frickin' big. So again, we're back to slightly boring for the ice chart. Since it's again a limiting reactant, super frickin' big reaction, and there's no real K to solve. All right. My second reaction following this is the acetic acid reaction. But again, my acetic acid reaction is not right, super freaking big. It's not friggin' big, right? It's a weak acid dissociation. And so I'm going to have to solve the K equation, right? But please note, right, we saw this when we were talking about buffers before. If I add a strong acid or base to a weak acid or base, I actually make a buffer, as long as the strong acid or base is the limiting reactant, because really beyond quote unquote neutralizing the acetic acid, right, on the product side, the hydroxide also made the conjugate, which is the acetate. And so at this point, it is still just technically the Ka of the acid, right? But again, my second reaction always starts where my first reaction ended. And since my first reaction ended with a little bit of acetate, my second reaction starts with a little bit of acetate. All right. And so, in fact, I have a buffer, right? And this is really the beginning of why I feel like the titration curves ultimately, right, best summarize all we've been talking about with acids and bases. I have multiple acid-base reactions. I have to use K to sort them out, right? I started with a weak acid. Hey, there's a Ka problem. Once I start titrating, I have a buffer problem, right? Now, you know, I can Henderson-Hasselbeck it. You could also just solve it as it is. I mean, it is ultimately just a Ka problem, right? But, you know, we have a shortcut. We might as well use it. And so my pH has now jumped to 4.14. You might note this is also something of a difference from my strong acid, strong base titration, right? The pH has moved much more, right? We'll look at the numbers again in a minute, but for the strong, it went from 1 to 1.17, right? For my strong weak here, it went from 2.87 to 4.14, right? That is really the buffer setting up, right? If you think about the buffer in terms of Henderson-Hasselbeck, right? Unless you have extreme differences in the conjugates, your tendency is to get pHs near the pKa, right? If you've got similar, and by similar, I really mean same order of magnitude. If I've got similar concentrations of the conjugates, the log is going to be, you know, somewhere around 1, right? If they were equal, it would be 1. And so that log term should be a small adjustment to the pKa, again, until there's an extreme difference in the amount of the two conjugate species. And so unsurprisingly, right, I jumped up to 4 because I'm trying, at least initially, to get to the pKa value, if I may anthropomorphize my reaction. Yes, no, maybe. And again, it keeps doing that for a little while, right? If I had a little more hydroxide, again, my super freaking big reaction is still going first. The hydroxide is still the limiting reagent, but what I'm doing is changing the ratio of the conjugate, right? Every time I have less acetic acid, I also have more acetate. And so it's still a buffer, but that log term, the ratio has changed slightly, right? So the pH has changed slightly, right? As it got closer to the pKa, there's no need for it to take a big jump again. And if I add a little more, I now have more acetate than acetic acid. I'm now on the other side of the pKa, but again, I'm still just gradually changing. If I do it one more time, right, I'm now at that 80% point where I've converted 80% of my acetic acid into acetate. My pH has gotten fairly high, all things considered, right? I started at 2.87, I went to 5.34, right? That's a change, of 2.5 pH units, right? If you recall, for my strong, I went from 1 to almost 2 in that same period of time, right? So I do get bigger changes with the weak acid, right? And of course, at this point, I'm going to get a really big change because if I add a little more hydroxide, I'm going to run out of acetic acid, right? And so obviously, when your calculator is screaming at you that you can't divide by 0, much less divide by 0 and then take a log, this is when your calculator really, revolts and starts smoking, right? Not a buffer anymore. And so as not a buffer, Henderson-Hasselbeck is of no use to me, right? So no more shortcut. Again, however, it's really just a question of what's still in the beaker, right? Before, the only thing I had left, right, were spectators and water, right? Because, I've been sort of ignoring the spectators, but, I will save you the dizzying journey by flashing back, right? When I was doing HCl and NaOH, right, I had Na plus initially as a spectator, right? And then I also made Cl minus in the neutralization reaction because HCl plus OH minus, right, gave me water plus chloride, right? The chloride as the conjugate base of a strong acid, again, classic spectator, right? It's again a little different here, right? I still have sodium floating around as a spectator, right? However, unlike the previous example, right, whereas the chloride was a spectator in the previous example, the acetate is not, right? Because of course, acetate also a conjugate base, but it's a conjugate base of a weak acid, not a strong acid. Right, and so I actually have essentially a salt problem, right? I have the conjugate base. I mean, that's really what defines my salt problems. I have a conjugate acid and a conjugate base. In this case, the conjugate acid would be sodium, which is still a spectator, but the acetate is a legitimate conjugate base, which is a weak base. And so the only acid left for it to react with is good old water, right? And I get an honest to goodness KB reaction with the conjugate base of the acetic acid. And so, as always, all equilibrium problems have 3 parts: balanced equation, ice chart, K equation, solve. And if I do that, and hey, my assumption works, assume x is less than 0.05, cross multiply, take the square root, I get 5.27 times 10 to the minus 6, right? Which again is a concentration of hydroxide and is usually the case. Since I care about pH, the hydronium comes from good old Kw, or 14 minus the POH, right, which in this case is a pH of 8.72. Right. So again, the other big difference here between my strong and my strong weak titrations, the pH at the equivalence point is not 7. Right. In fact, it's never 7 if either the acid or base is weak, because what you have at the equivalence point is the conjugate. And the conjugate, if you're weak, is not a spectator. And so, in fact, the pH at the equivalence point in this case is 8.72. Oh, perfect timing. After that, there is no difference between the strong acid and strong base and the weak acid strong base, because at this point, I'm just adding excess NaOH again. And so again, my pH is just going to be determined by the excess strong base, right? And so after the equivalence point, right, these are identical. Obviously, if I switch it so it was a weak base with a strong acid, it'll be essentially the same but opposite. And the pH at the equivalence point would be less than 7 rather than more than 7, right? But the same basic trend exists, right? I still get a fairly rapid rise as I go through the equivalence point, but one, the equivalence point is no longer 7, and two, my rise isn't quite as rapid, right? Because if I have the weak species present, right, I'm actually much higher going into that equivalence point rise than I would be if it's strong, right? And that is, again, something of a general rule. This is something of a horrible drawing, but, right, if you look at this weak strong titration, it's got everything in it. This was a weak acid Ka, right? This whole region was a buffer. The equivalence point was the Kb of the conjugate. And for good measure, this was just a strong base, right? And so, you know, as I advertised going in, my titration is really everything we know about acids and bases in one analytical technique. Yes, no, maybe. I wanted someplace to draw, right? And so if you, oh, class is over. If you compare the two, I'll tell you what, I will draw it on the screen for those of you at home. I will draw it on the whiteboard for those of you in class because it takes too long to switch over. If I go strong, strong, right, it looks like that. If I go strong, weak, right, it always starts higher. It always jumps up higher. And so you have a compressed equivalence point region. And so the shape is somewhat different, right? But again, those differences are representative of the class of the reaction you're doing, right? If they're strong, strong, right, there's always an equivalence point of 7. There's always a very gradual start and a very gradual end, right? If I go strong, weak, right, I'm always starting higher because I don't get complete dissociation at the beginning. I always go through that buffer region, which gives me a slightly greater increase than would be true for strong, strong. And then I have a compressed equivalence region because I'm going into it at a higher pH than I would be if I was strong, strong. Happy Friday. Enjoy the return of winter. I will try to grade as many of those projects as I can this weekend. So far, they've been pretty good.
I have a question, Professor.
I mean, I think this
so.
Sorry, my roommate was talking.
So for a strong, weak combination, is the equivalence point pH